Okay, so yeah, today I will talk about the Paxos quorum reads, or the linearizable quorum reads in Paxos. I think this is the first time in our reading group when a person who actually authored the paper is going to present it. So that's new, I guess. Yeah, this paper appeared in Hot Storage 19. So yeah, last year in Seattle, Renton. Yeah. Yeah, and this is pretty much the same presentation that I was given back at Hot Storage. I will start with a quick recap on what is Paxos, right? So Paxos is this very robust, really good algorithm that solves distributed consensus problem. And Paxos is used frequently in like strongly consistent systems to support the replicated state machines. The Paxos-based replicated state machine would operate in these 3 rounds that you see on the screen right now, in the 3 phases. In the first phase, the leader election phase, that's the phase 1 of Paxos, one node is going to establish itself as the leader to propose the command, to accept the command, to tell what command should be accepted in the Paxos round. The way Paxos does it is it has this ballot numbers to guarantee that there is only one active leader at the same time. And it requires this majority quorum in the phase 1 to agree that, hey, yes, you can be the leader with this ballot number because we haven't seen anyone else with the higher ballot number. So yeah, so this is this phase 1 right here. The majority says okay, and a single node emerges as a leader. Once this has happened, the leader can tell the followers to accept the value. The value that the leader has to tell to accept, it may be either a completely new value if it hasn't learned, if the leader hasn't learned of some old value that needs to recover in phase 1, or if there is such a value that needs to be recovered, it has to be that value from learned from phase 1. And finally, for the purpose of the replicated state machine, the leader is going to tell the followers to commit this, essentially commit this operation, so that the followers can apply it to their replicated state machines, their state machines. So these 3 phases, they kind of constitute the meat of how the Paxos operates in many of these distributed databases, you know, like Cockroach, Google Spanner, and so on. Now, of course, this is very chatty, so you know, the Paxos on itself is not really used often, right? So for one, you know, having to repeat phase 1 all the time, it essentially doubles the cost of the protocol. So instead of having to elect a new leader for every single new command, MultiPaxos, the most common optimization to Paxos, it elects a single stable leader, right? So we run this phase 1 leader election only once, and we keep this leader for as long as we can. As long as this leader is alive, you know, we can keep using this leader for multiple accepts, for multiple commands. So this leads to the phase 2 of Paxos, where now we're going to repeat it many times, right? So we did 1 leader election, and now we can repeat phase 2 many times. And finally, this phase 3, the commitment message to tell the replicas to apply the command to the state machine, it can be piggybacked to some next phase 2 message. So for a lot of practical purposes, we kind of boil down Paxos operation in a happy case, right? In the case when we don't have to run leader election because of the crash failure, so we don't have to recover the replicas for you know, the state machines for some reason. You know, we often boil down to just this one RTT kind of communication. where the leader is going to talk to the followers are going to acknowledge, and that repeats for as long as we have this stable leader. So unfortunately, this still has some problems for Paxos. Mainly, we have this single leader that talks to many nodes, right? The single leader is going to send the message, it's going to broadcast the message to all these followers. And it will also receive these individual single messages from every of the followers saying, hey, we accept your value, you're good. So this essentially creates this bottleneck at the leader where it sends a lot of stuff, it sends many messages, it receives many messages. Compared to the follower, if you look, a single follower will receive one message and send one message in a given Paxos instance or communication round or Paxos slot. So the leader has a lot more messages going for it than the follower nodes. So this makes the leader the biggest bottleneck in the system. Yeah, I already mentioned that Paxos is used in quite a few databases, quite a few systems. So the Paxos itself is like a very generic system. So it doesn't have a notion of how do you read from Paxos, because Paxos is just consensus on commands and operations. So the read operation would be just another command. You apply it somewhere in the log, and you can read from that point in the log, or from that state in the state machine. So by itself, Paxos and Paxos-based replicated state machines, they don't have this notion of what is read, because everything is just a command. But we do need to, like for practical purposes, right? And in databases, we do a lot of reads. It's not always, the state mutation that we have, that we commit in the log. So the operations would be the writes, we change some state of the state machine, and the reads, where we want to retrieve that state. And the most common ways of reading in the Paxos-based systems, right, in the Paxos-based replicated state machines, would be either reading from the leader, because the leader has the latest knowledge. It always has the latest knowledge, right? So if you decide to read from the leader and not run the Paxos round, then you need to have a lease to protect the leader from the failure. So in this kind of system, we'll be introducing some timing assumptions based on the lease, and the recovery is going to be based on that lease timing assumptions. But we can do the reads very efficiently from just a single node, the leader. Now, some systems actually say, we're not going to read from the leader, because the leader is already the bottleneck, as we saw. If we're going to write from the leader and do all the reads from the leader, that's going to be really bad. It's not really saving too much of a bottleneck for us. So, for example, Zookeeper, it allows to read from a single replica, from any replica, any follower. The problem with this read is that a replica may be stale, right? Because we need a majority quorum to commit the operation. So if you're reading from some replica that was not in a majority quorum, that maybe is lagging behind, the leader may have advanced to next operation, but your replica may still not receive it or applied it. So there is always a possibility of reading the stale data in systems like Zookeeper that read from a single arbitrary replica. The third option, of course, if you don't want to do the regular Paxos operation, is to try to read from a quorum of replicas. And this is exactly what we do in the Paxos quorum reads. Unfortunately, it's not as simple as just reading from the majority of replicas, because because we have the leader that may still be slightly ahead. So you may end up in a situation where an operation has committed at the leader, but the phase 3 message, the commitment message, hasn't reached the replicas yet. So the write may have succeeded, the value have changed, but the consecutive read may still read the old value. So that will violate the linearizability assumption of our strongly consistent replicated state machine. So in PQR, we designed the quorum read system that will not violate linearizability. The basic idea of PQR is that instead of reading the value that has been already applied to a state machine from the majority of replicas, we want to read the operation. We want to read at the slot number that will be applied in the nearest future, right? So because this value has not been applied, we know for sure that at this point, we kind of safe. It's still in the future. Now, if we want to read something in the future, of course, we'll have to wait for this future time to reach us. So PQR, in a sense, operates in two phases, right? So we do the quorum read phase, where a client is going to reach out to a quorum of nodes. So the client is not touching the leader. It's not causing more bottleneck issues for the leader. The client is going to reach out to the quorum of followers, and it will ask for the latest accepted slot number. So the latest accepted means that the replica has received this phase to A message. It may have replied already back to the leader, but it hasn't gone to the phase 3. It hasn't applied it to its state machine yet. So we read the latest accepted value from the quorum of nodes. At this point, when this quorum read phase has happened, we essentially know, okay, this slot number is going to be executed soon, and our read is going to wait for this. So we are artificially delaying the read until this future write is going to happen to preserve the linearizability. So this waiting happens in the rinse phase. So once the client has received the slot number, all the client needs to do is read any single follower, just one follower, to see if this particular slot or some future slot, slot greater than the one that we have observed in the quorum read phase, if it has been executed. Right. So if it has been executed, it means that we have successfully waited, we have successfully delayed the read operation up to the point that it now can read the proper value and be linearizable. Yeah, this is kind of the diagram of what I just explained. Right? The client is going to reach out to followers. It's gonna receive some slot numbers. It will pick the maximum accepted slot from at least a quorum of nodes, and then it will wait for this slot to be executed. So obviously this is kind of slow, right? So in the beginning of the talk, I said that a lot of the times in regular Paxos, we kind of boil it down to just one RTT. And here we have introduced at least 2 RTTs and maybe even more if more waiting needs to happen in the rinse phase, because we may need to repeat it multiple times. So in a sense, we are removing some bottleneck from the leader, but we are adding all these messages and all these RTTs and hurting the performance. Yeah, so this is the example of how this two-phase PQR works, right? So we can, the green one is the executed slots. The purple one are the slots being accepted right now. 5 is the last accepted. So if the client is going to read from, let's say, some quorum of followers, it may read, may read 4 and 5. If it reached this node, then the maximum accepted slot is 5. Hasn't been applied to the state machine yet, so obviously it cannot be returned yet. But we can wait, and sometime later, all we need to do is reach out to this one, to any node, see if it has executed the slot 5, and then we can return the slot 5. But as I mentioned, this is 2 RTTs in a best case scenario. Luckily for us, oftentimes we can do better than 2 RTTs. We can actually reduce the communication down to 1 RTT. And the reason why we can do this is because in the simplest case, consider the simplest case when we have no progress in Paxos-backed replicated state machine. When we have no progress, then the latest accepted slot of every single follower is also going to be the latest executed slot at all of these followers. So if we read the quorum of followers, and they all return the accepted slot being the same as executed slot, then we know that there is no other operation at this point in progress at the stage where it already reached the followers. So it's safe to return this slot 7 right away, right? Because there is nothing else is going on. So obviously this happens when there is no progress. In a real practical system, you cannot expect to not have progress, right? So if you have a database, you will you will write different I don't know, maybe different documents, different key value pairs, depends on what your database is. But you will have some progress that will be appended to this one single shared log. However, this kind of no progress optimization, despite having a single shared log for all the objects in this database, right? This no progress optimization can be applied on a per object basis. So if you read, for example, that object A last accepted slot was 7, last executed was 7 from the majority at node, it doesn't matter if you have slots 8 and 9 on different objects. You still guarantee that at least on this object there is no ongoing operation. So with this kind of optimization in a database kind of scenarios, we can often do PQR in one RTT. And yeah, so our evaluation in this paper, like in this case, we performed a write-heavy workload, quite honestly, because this is the workload that works best with the PQR. But at the lower write ratios, it still has some benefit as well. Essentially, by removing the bottleneck, by removing all the read workload from the leader, we can now push more write workload through that leader, right? So we can balance the load between the nodes better by shifting a lot of the read burden to the followers and the client. So this, like in this write-heavy workload, allowed us to have, up to like 25% better throughput compared to regular Paxos, and about 10%, 15% better throughput than the Paxos read from leader, just because we are not tagging this leader all the time for this 25% of the writes. As I said, we observed similar results at other write ratios, but they actually tend to diminish a little bit. So, because obviously, if we don't do any writes, if we do 0 writes, then essentially you do PQR all the time. There is no progress, always send one RTT. If you do all writes, then you never do PQR. So there is like a sweet spot where the quorum read optimization will be the most beneficial. Yeah, this is the latency experiment at this point at the 25, 50, and 75% read ratio. So 25% Paxos read from leader is doing slightly better than the PQR in terms of latency, but at the higher write ratio, the PQR is a little bit faster. A lot of the times that's because it doesn't bug the leader who is already bottlenecked, and it still can do it in one RTT. So yeah, in conclusion, it helps PQR, Paxos quorum reads, help balance the load between Paxos leaders and the follower nodes. And that's the entire idea of this, of this little paper, to see if we can try to have a better balance. And we do this by uploading the leader that supposed to serve all these operations. We upload the leader from doing non-mutating operations, read operations. And this allows us to better utilize the load on the followers, on the follower nodes, who tend to be less stressed, so to speak. So yeah, that's the little presentation. I'm going to stop the recording now.